found this with some of our very thin overlays, the paving speed can become too great. It becomes less of a material supply issue and more of a, we're progressing too fast, now we can't saw cut quickly enough, now we can't get the texture and cure on quick enough, and there's some innovation that needs to happen behind the paver now, I think. Once we pave very, very thin, they can go very quick. So far we've talked about jointed plane concrete pavements. We're going to touch now on pervious and roller compacted. Pervious concrete, if you're not familiar with it, it's a concrete pavement with a bunch of holes in it. We take mid-size aggregate, coat it with just enough paste to coat the outside, essentially, to get them to stick together. But water can very easily pass through it. Is there pervious concrete in Chile? I've seen some in Colombia. It's a niche product, really. It's not something that you would use all over the place. We use it on shoulders, but it's not the most applicable thing. It actually was first innovated in Europe for house construction. Because it has so many voids, they would form up and build a wall, and then they would basically close off the outside with grout. And then they had a bunch of air pockets in there, just like any other insulation, to insulate the house. That's where its roots come from. With this particular type of material, the mixture design is very important because the variation you can get with a poor mixture design, considering the source and the ability of the source to produce the aggregate in a uniform supply, is very important. Now the challenge is we're trying to place to the desired density. If we overcompact it or somehow place it at a higher density, it starts to lose its permeability. And because it has so many voids, there's a lot of paths for air to get into it. So if it's a windy day, we really have to protect the surface or air will very quickly get in there and dry it out. So when we're talking about construction of these pervious concretes, we generally have a geotextile to help separate the subgrade soil from our reservoir layer. And this stone, open graded, clean stone reservoir layer can become very thick, even several meters, depending on how much volume of water we're trying to contain while the subgrade soil processes that and allows it to go back into the water table. So here's a photo of it. That's pretty thick. That's about up to there. But it's just like conventional fixed form paving. We set our forms. We use a roller screed to strike off the surface. Our forms might be wood or metal. We dampen the subbase to satisfy its water demand. We place the pervious concrete within the forms. We move it around with concrete rakes. Here they've got a tamper just to work the edge a little bit. It gets stricken off and cured. Now we have to use a conveyor. You can't pump pervious. It has too many voids inside of it. We can do all this sort of stamping and coloring and architectural things. I'm a pavement purist, and I like my concrete gray. But the tools that they use, see them all right here. Square shovel, roller screed. They've got an extra roller here, a tamping device, a rake, and here is the joint forming tool. It's not a saw. It's what we call a pizza cutter in layman's terms. It just creates the weakened plane by moving aggregate out of the way. So we're going to see them very quickly apply all this. So they get that equipment out in the field. As I told you earlier, fill the screed up with some water to weigh it down. And in a very, very narrow window, do a lot of work very quickly. It's an orchestrated dance. This is very labor intensive. See all those people? This is not a demonstration site. This is an actual project. And there's this much labor. They're getting the concrete. It's being conveyed up over the top of them, spread out as uniformly as possible. So the amount of work necessary to move it is minimal. Because segregation is bad for pervious. That's how we end up having a closed surface. Spread out the material, use a concrete rake to spread the surface only. We're trying not to have to move it. It gets screeded off. They don't close the surface. They use a linseed oil or some other cure and apply a plastic cover to it, all within about a meter. I guess 3 meters, sorry, all within about 3 meters. Here they have their saw forming or joint forming tool, so they'll peel back that plastic and form those. We'll see that in a second. So if we have to move the concrete, we use these rakes to pull it. We have a very small head of concrete rolling in front of that. We don't want to see too much. In this particular photo, they're walking on top of the fresh pervious concrete. That's going to compact it, densify it, and make it so it's not pervious. So you have to stand out away from it whenever it's being constructed. Some photos of the roller screed. It's the same piece of equipment that we use for conventional paving. But we want to see a nice uniform surface there, not a bunch of closed off pockets. Construction methods can vary. Here we have truss screeds. Down here on the right, we have a laser screed placing the pervious concrete. So there's a lot of different methods. I've even seen people pave pervious concrete with an asphalt paver. So it's pretty much any method that we use at this point. We compact it. And many times they won't even compact it at all. But if they're going to compact it, the easiest thing to do is to have your forms of a certain thickness and then just have thin riser strips tacked on top of that. So we finish off the surface level with the riser strip. In the bottom right photo, we remove the riser strip. So we have this much concrete sticking above our form. Now, if that's of uniform thickness sticking above and we compact it all, we get the same density across that, as long as we don't somehow close off the surface. But we do need to sometimes compact it to get density. We want a nice uniform surface, again, not like the bottom right. We have these pockets of built-up mortar in spots that will impact its permeability and probably its freestyle resistance and performance. Along the edges, we use a hand tamper just to make sure we get the compaction we're looking for. And they can round or chamfer the edge as they can with fresh concrete. So that plastic cover needs to be on there in about 3 meter space. It's relatively quick. Photos of jointing. So similar to the screed, this is weighed down a little bit with water, rides across the surface, and just pushes in there like a pizza cutter would. Cut up a pizza. So we used to not joint pervious concrete at all, and then everybody started jointing it to make it look more like conventional concrete. I think now we're back towards not jointing it as much. If you're not putting steel inside the pavement, how important are joints? Unless you intend to maintain them. In pervious, the design life is not 30 years. Nobody thinks we're going to get 30 years out of this solution. So it'll probably be removed and replaced. But pervious concretes, from a design perspective, will not fault. It's just impossible for that mechanism to happen. So having a crack versus a joint, there's really no reason to be concerned about a crack. Some more photos of joint forming. We are now saw cutting pervious concrete as well, using the same means as with conventional concrete. There was a lot of concern early on that that might cause a lot of raveling or other performance problems. That hasn't been the case. It can be saw cut just the same. For longitudinal joints, if the section becomes wide enough, you can place a longitudinal joint with a pizza cutter form on the screed. That's a roadway to, what's that to? It's like a veterinary clinic. Once we remove the forms, we really see that it is pervious. It looks like a Rice Krispie treat in nature. Water can easily pass through it. And then we have to cure it. Now we have to cure this for 7 days. There's no way around it. If we're using SCMs or fly ash or slag cement, we need to cure it for about 10 days. So it needs to be covered on all sides, not just the surface, but the exposed edges as well. some more photos of carrying on a pretty large project. So we're seeing this more for parking lots, low volume roads. We've used it some on highway shoulders, but it is still relatively not that common compared to conventional concrete. Photos of good practice on the left, plastic's way down, it's not going anywhere, and bad on the right. So here's the final product. Trails, car dealerships, even firehouses. And the firehouses, they wash the trucks a lot. So they're constantly adding water out in front. This is a low-volume road in Minnesota. So we've solved the freeze-thaw issue. It's not an issue anymore. A residential area with an asphalt road and then parking lanes impervious. I think of some of the more innovative applications. We have a big parking lot at a university where the architects decided that this was something they wanted to do, and the civil engineers found out how to make it happen. But the parking lot is pervious concrete, and it captures the rain, and they use that rainwater to flush the toilets inside the stadium. So it's not a typical pavement approach, but it has some benefits from other perspectives. So now we'll switch and talk about roller compacted concrete. I see this as the future in a lot of regards of concrete pavements in the world. It uses asphalt paving equipment to build concrete pavements. So everyone has asphalt paving equipment. Not everyone has slip-form pavers and other concrete equipment, but this is really catching on globally. And once we get the issues all resolved, I think it will catch on even more quickly than it already has. And we're basically using a zero-slump concrete, so we don't need formwork. That helps drive down the cost some. We're using asphalt paving equipment. Again, that's readily available. We have to have a good enough support system, good to subgrade and subbase for the RCC, roller compacted concrete, to be compacted against. So it has to be strong enough to compact up against. We can use all types of concrete mixing operations now. RCC can be mixed with ready-mix trucks, with conventional batch plants. We can use continuous mixers, horizontal shafts, or pug mills. So it's very versatile in that regard. Won't dwell too much on those things in the interest of time. So the support preparation really isn't much different than what we already do. We need to build up a strong enough system that we can build on top of it. Now when it comes to material transport, because the concrete that we're using is zero slump, it's very dry. We've essentially taken out some of the coarse aggregate and added in more fines to help us with the density side of things and compaction. But it's a very dry concrete, so when we transport it in something like an in-dump truck, we need to keep that covered. We have a very short window of transport and placement. But the trucks back up to an asphalt paving piece of equipment, standard density or high density, that passes through the paver and gets compacted. Now with the high density pavers, we're finding we can get 98% of the proctor, the required density, directly through the asphalt paving equipment, and we don't have to use any sort of rollers. But with the standard density paver, you still do have to use the vibratory steel drum rollers. So once it's passed through the paver, some more photos of that, just the paver compaction. We use vibratory steel drum rollers, rubber tire rollers, and other rolling methods to get the final compaction that we're looking for. So it is essentially the performance of a concrete pavement, especially if your standard is already undoweled, jointed plane, but using asphalt paving equipment to accomplish the task. The concrete tends to be a little bit stronger than a conventional concrete mixture. It tends to be a little bit lower cost, has a lower cement content than conventional concrete. And because we're not using forms at all, there's no steel inside of it, and other aspects like that, it tends to be relatively low cost and high production volumes achievable. So we've seen it a lot for industrial applications, port facilities. It's just now making its way into low-volume roads, residential streets, highways, and things like that in the U.S. Now, similar to asphalt paving, if it gets to be too thick, we have to place it in 2 lifts because we can't get compaction through too thick of a section. So we end up having to place it 2 lifts, one at a time. The surface traditionally has looked kind of like a gray asphalt surface. We're tweaking the mixture, making it more well-graded. We're getting a more closed surface. There are now integral admixtures and topical methods of closing the surface and broom texturing it, just like conventional concrete. So we can now get the surface friction that we're looking for roadway-type applications at relatively high speeds. We're not seeing it yet on highways, but for lower volume and medium volume roadways, it is being applied now. Curing is just like for conventional concrete. You can use a white pigmented curing compound. You could cover it with plastic. Same challenges for curing and the other ancillary technologies exist. This is very poor curing compound application. So the same exact challenges. I guess another big benefit, if you look at the curing pattern here, you might notice that it looks like somebody painted themselves into a corner. The last, or maybe the first round was right there. With roller compacted concrete, as soon as it's compacted, you can put some traffic onto it. I guess that's a benefit I didn't get around to mentioning. So as soon as you've passed by someone's driveway, the rollers have passed by there, they can drive on top of that and into their driveway. There's no real cure time because the material itself builds up a mechanical resistance to vertical forces by being so compacted. Sometimes we allow it to naturally crack. There's some low-volume roadways where we allowed that, especially if we're going to overlay it with asphalt. Longitudinal joints can be tricky because we do have to compact up against adjacent placements that we've already placed, or sometimes we're going for almost immediate compaction between sections if we're somewhere like a port facility and paving a lot at once. But we can make those look very nice now as well. Saw cutting is essentially the same as for conventional concrete. We use both early entry and wet conventional saws. The same saw cut depth and other requirements. Some people are suggesting that we can have a further joint spacing. And that's probably true for the same opening. Because it has a lower paste content, there's less cement, even though there's more sand, it has a lower cement content. Its shrinkage tends to be less than that of conventional concrete. So if you saw cut it at the same spacing as a conventional concrete, the joints won't open as much for roller compacted. And we're relying only on low transfer efficiency by aggregate interlock here. And even still, in most areas, they're extending the joint spacing out to 5-6 meters. If you're overlaying it with asphalt, here's some photos. They're below grade on that manhole cover. They've got a spot where they're going to saw their longitudinal joint, but it looks like they'll just let it crack naturally transversely there. Because we have diamond grinding equipment so readily available in the US, we're starting to see RCC ground to get us a smoother surface, to get us the frictional properties that we're looking for, and to get it so that we can place RCC on higher speed roadways. So it's the same operation as with conventional concrete as far as diamond grinding this. Some photos of the final product. Again, in the industrial space, ports and other heavy equipment applications like that, because of its higher strength, is really why we've seen it be applied initially. It originated in Canada. They started, well, I guess the first trials were in Sweden in like the 1950s. It kind of fell dormant. In Canada in the 1970s, they really started to apply this for log sorting yards and other heavy equipment type applications. In the US, our military started to adopt it in about the same time, 1970s, 1980s. And they used it for tank hard stands, trails where they had tank training operations, where they had to actually rotate the tank onto one of the tracks, pivot on the nose, do weird things, and no other pavement could hold up to. But because of the higher strength of RCC, it could do that. After those first sections, the technology kind of sat dormant for about 20 years until we had proof that it could last. And now we're at the point where everybody believes this is a third pavement type that can last 20, 30, 40 years, and we're starting to see it much more broadly applied. Some salt storage pads and snow storage pads at Denver's airport. So they'll store salt, and sometimes whenever they're using the salt or they need to move snow into that area, they'll push snow into these massive areas. Some of their taxiways are RCC now as well. So that's a freeze-thaw area, and it's worked very well. Some more intermodal or truck distribution facilities. Some more port projects. Now, even though these sort of intermodal facilities are servicing truck traffic and they lead from a road to this sort of facility, the loads that you see in these applications are much, much different than roadway loadings. A device like this is picking up one single container, lifting it very high into the air and stacking it onto others, but the loads that it has on those front tires are quite a bit different than what a truck would impose. So there are special considerations when it comes to design. Lastly, industrial concrete paving. I have a few comments on this. Not too much. We use the same practices, slip form and fixed form paving, as we do for roadways. We use dowel bars just the same if there's channelized traffic, but because once you enter into an industrial facility, you can't predict which way the traffic is going to go most of the time, so very often we will not dowel. We'll use a concept called the tension ring, which for the designers in the group, we essentially use tie bars around the entire perimeter of the facility to lock the system together. Or we'll use these PD3 or tapered plate dowel bars, which allow for some misalignment. So that was mentioned earlier. I don't think I have photos of those in there. No. If we're slip forming, we place in strip placements in these very large applications. We do the same thing in airfields. So we'll place a strip, skip a strip, place a strip, and so on, and then come in and fill in the middle sections, which they're starting to work back the other direction down here. You can see dowel baskets placed out ahead. That's not always the most economical means. And if you tell the contractor that this is going to be construction joint after construction joint in that direction, they have to do a strip placement like this. Laser screeding is much more common these days in these sort of applications where they're using laser devices to place in two directions at once. So instead of strip placements, we're building in the X and Y at the same time, and then we're just making a massive block and saw cutting that in both directions, like a sheet of graph paper. So when it comes to the design, if you get involved in these non-roadway type applications, just give some consideration to how they will be constructed. This is part of, well, I mentioned the differential deflection and bearing stresses as drivers for dowel innovation. This sort of strip placement is another key reason why they've gone to different geometries. Because what was happening is, if we place two strips with a gap in the middle, those strips will shrink. Now we place the strip in the middle. It needs to shrink as it cures, as it dries out and cools off. But the first sections might want to expand then when the sun comes out. So we have opposing forces which will cause cracking inside of the second placement. How wide are the strips? Depends on the operation. This looks like they're doing one width, one slab width, so maybe 4 or 5 meters wide. But they could place two strips, 2 lanes in one pass. It all depends on what their operations are. But when you do the strip placement, you end up with differential shrinkage in opposite directions. And what the plate dowels do is create a void that's larger than the dowel itself when the concrete shrinks around it. So it can allow for some lateral shrinkage or lateral movement without restraint. So So just by geometry alone. So there's been a lot of good innovation out of the industrial facilities for quite some time. Here's a case where the joint layout was probably going to dictate slip forming. It's an intermodal facility, but it's a constant width. It's going to be very easy for someone to slip that and very difficult for a laser screed to beat them on price. In this application, we have on the background on the right, they're slip form paving the entry access road. And they're paving the bulk area over here to the left. You can kind of way in the back see them working around those light standards. But they're using RCC on the more industrial portion of this section. So we sometimes mix things as well. Those may have been both designed as alternates. This could have been jointed plane or RCC and vice versa. And they just ended up with those being the cheaper of the two based on geometry and other concerns. So any questions on pervious or roller compacted?
Una consulta para pavimento drenante. ¿Cuánto tiempo se espera que se comporte como pavimento drenante efectivamente? ¿Y qué vida útil se le exige a esos pavimentos?
Develop effectively. Does he mean opening strength? So you're just about service life.
Service life.
Okay.
And the open the traffic, the pervious.
So I'll just answer both parts. So opening to traffic, it all depends on the local standards and the project requirements. If we have the luxury of allowing the concrete to cure for several days, a week, we won't use any sort of special cements or cement contents or anything else. We'll let the concrete process kind of happen as it will. Now, Roberto and I do you mind if I talk about our cement-based discussion at lunch or not? Is that okay? I don't know if there is something locally I should be concerned with. Cements have changed a lot in the last 50 years. Owners have really driven home this point of we want high early strength. So justifiably so, and it doesn't matter if we're talking about pavements or vertical construction or anything, everybody wants to open their structures sooner. Cement companies have responded to that by grinding cements finer and making other tweaks to get very high early strength. Now that's changed the fracture properties of concrete to a great deal. We're talking about vertical structures that are reinforced with concrete, that's probably less of an issue. But we're talking about pavements, and prevention of flexural cracking is a big component of what we're trying to prevent. It's a very big issue for us. So with that caveat, I would say that there aren't generally any sort of special tweaks for early opening or anything like that in 99% of the cases. And there shouldn't be. You should be using the standard over-the-shelf cement. As you go towards the more and more high early strength mixtures, you tend to introduce more of this concern for the brittleness of the mixture and challenges with crack propagation in the service life. It becomes stronger but becomes more brittle. That's the short answer. So reserve high early strength. If necessary, we can open to traffic with slip forming operations in the matter of 4 to 6 hours. There are repair materials now, such as pavement, that as soon as we mix it and place it, you can essentially start putting traffic on it. It's a very short work life that we have with the material. We have to get it into whatever hole that we're filling. We use that more for repair type applications, but there's no work window that we can't work with at this point. In the US, there's been, in the last decade, a massive push towards nighttime and weekend closures for construction. We don't have the fortune to go out and just be able to build week in and week out anymore and have full detours and closures. We're always working under traffic. So the mixture design tweaks, when we didn't really have time to get into the material side of things, are there to get you whatever you're looking for. Now when it comes to the design life, that's the engineer's choice. In the state agencies in the US, I believe in my next presentation I have a slide that shows you their expectation. And it's somewhere around 30 years. That's what they expect their concrete pavements to get from a design perspective. With overlays, some of the thinner ones, we initially thought 5, 10, 15 years. And we can design a brand new concrete pavement for 5 years if that's what someone is looking for. The precedent has been set that concrete pavements are a long life solution, so we're generally talking more in the 20, 30, 40-year design life. Now we've got about 3 different state agencies in the US that are looking for extremely long life solutions. Minnesota is one of them, and California is the other that are worth discussing. In California, they want a 100-year concrete pavement solution. And then they're saying concrete pavement because they've already ruled out asphalt as even possible for that. So they want a 100-year concrete pavement solution. Minnesota, they're more on the 50, 70 years that they're looking for. Now they're trying to do this to just build one pavement up front, especially in California where there's very high traffic levels, and then not have to worry about it. But to get there, their emphasis has become less on the thickness design and much more on the materials and the detailing in the design. So they're looking at Minnesota. They tried stainless steel dowel bars, which is very, very expensive. Those dowel bars found a way, to no one's surprise, to just grow legs and find their way off of the job site. Because their salvage value was so high, they just kept getting stolen from the job. It makes it difficult to build a pavement when you don't have the dowel bars that you're looking for. They're looking for the same thing now in steel. Should we have some steel that's stainless steel as well in our continuously reinforced designs? So it's all about what the owner is looking for. But we now have, I guess, Illinois DOT, or Illinois Thruway, is looking at 75-year design, I believe, on replacement of our loop road around Chicago as well. So it's just what the owner is looking for. Standard, 20 to 40 years, 30 is probably right in the middle for concrete pavements. We can design down to 5 or 10 years if that's what you want. And we're finding now that 50, 70, 100-year design life is conceivable based on the proof that we have of performance so far.